Okay, hello. This is our first of our lessons where we're going to be going through the review topics in the various review units, mainly for Math 038, 052, and 053 students. There will be a lot of overlap in these as well with various O2 level courses where because most of the review material is stuff that was covered in those O2 level courses originally for you, for those of you who are in them. Sometimes these lessons will also provide some help with the stuff that you're currently learning. So for this particular lesson, if you are in Math 038, this is going to go through what you would look at in all three of R1, R2, and R3, those three sections. If you are in Math 052 or 053 and starting on the basic review unit, this looks at the first half of section 1.1 and part of section 2.3. I know that's a bit funny, but the basic review chapters 1 and 2 in Math 052, 053 don't they do a bunch of other stuff before they get to the decimal work, which doesn't come till 2.3, whereas in 038 it starts right in on the decimal stuff. So let's jump right in here. There we go. So the first thing we want to talk about is place value, and this is what you would call a place value chart. And if you look at it, you see everything stems outward from, well, there's the decimal point right there, but actually all your naming, if you look carefully, stems outward in both direction from the ones. So everything over here is to the left of the decimal, makes them big numbers. Everything over here to the right of the decimal is small numbers. Yeah, there's the decimal point, as we said, but there from the ones is where we start to name our decimal places. So if we go to the left and right of the ones, we have the tens column. So every number in this column is worth 10. So if you have like the number 37, the 3 represents 30, right? It represents 3 tens. And then on the other side, we have the tenths. So a number there in so if you had like a 5 there, that would represent 5 tenths. Or if you had a 1, it would represent 1 tenth. So a fraction of a whole number. If we go over each direction again, we have the hundreds on the one side and the hundredths on the other, the thousands and the thousandths on the other, and so on. So if we were to take a number like this, and we are asked to fill it in onto that place value chart, you simply work your way, you find that decimal point right there, right? And then everything to the left of the decimal, everything to the right of the decimal simply slots in all the way left and right. So, the 7 is in the ones column, and then 1593, right? 1593. And then to the right of the decimal, 698204, 698204. Everything just drops into the right box. And now you can quickly see what the name of the place value is for any given digit. So if a question says, what digit is in the hundreds position? The hundreds right there, well, that's a 5. What about the thousandths? Not the thousands, but the thousandths. Thousandths right here looks like an 8. So this is handy, especially at first, to help you make sure that you don't make little slip-ups. The most common mistake is people count from the decimal instead of from the ones. So they think, oh yeah, over 2 is the tens, so over 2 is the tenths. Actually, no, over 2 from the decimal is the hundredths, right? Whereas over 2 from the decimal is the tens. That's confusing. Instead, count from the ones. 1 this way is the tens, 1 this way is the tenths. 3 this way is the thousands. 3 this way is the thousandths. What if they said, what positions are the nines in? Well, there's 2 nines. One of them here is in the thousands position, and the other one here is in the hundredths position. You can do it, once you get good, you can just look over here, right? 1, 10, 100, 1,000. Oh, the 9 is in the thousands position, and this way, tenths, hundredths. The other 9 is in the hundredths position. So that's the basic idea of place value, and there will be some practice in your books on that. We're going to take that now and we're going to use that to talk about what we would call expanded form. So when we write a number like 5,136, this 6 here just represents 6, but as we said before, that 3 doesn't represent 3. That 3 actually represents 30, right? 36. So that 1 there actually represents 100. And that 5 there represents 5,000. So expanded form, we recognize that this number, it has 5 thousands, 100, 3 tens, and 6 ones. And so we write it in expanded form like so. 5,000 plus 100 plus 30 plus 6. If you add those 4 numbers together, you get 5,136. So we've separated out each of the place values and show what it actually means. Let's write 380,000 in expanded form. Well, we have a 3 in the 100,000s position, and we have an 8 in the 10,000s position, and all the rest are zeros. So I guess technically 300,000 plus 80,000 plus 0,000s plus 0,100s plus 0,10s plus 0,1s. Of course, adding 0 doesn't do anything, so we don't really need to write those down when we write expanded form. All we got to do is list the ones that are actually affecting the number, and that is the 300,000 and the 80,000. So that, right, what we've left uncrossed there would be the expanded form. What I want you to notice, and we're going to be talking a lot about zeros here for the next little while, and when zeros are important and when zeros are not important. So in 380,000, when we write expanded form, we don't need to write all those zeros. 300,000 plus 80,000 is completely sufficient. That is 380,000. But when we write the number 380,000, we can't just write 38. We can't juts, right? Little typo for me to correct later. We can't just write 38, right? We have to put those zeros down because 38 is not the same as 380,000. Those are different numbers. So the zeros are important. They need to be there, even though when you list them in expanded form, they don't actually add anything to the number. They are critical in telling people what number you're talking about. Now, this number here happens to be the distance to the moon. I picked that on purpose. So if you say, how far is it to the moon? Well, it's not 38 kilometers, that's for sure, right? It's 380,000 kilometers. Let's try another one that has some zeros tucked in there, 785.32009. Let's write that in expanded form. Let's start on the left side there with 700s, 8 tens, and 5 ones. Like so, 700 plus 80 plus 5. Now we got in the 10ths position 3 tenths. And when I last did this lesson, at the end someone said, I'm confused about why they call them the tenths and the hundredths and the thousandths, tenths, hundredths, and so on. Basically, the idea here is if you take one spot on your number line and you divide it into 10 equal pieces, 0.3 is 3 tenths of the way along the number line. That's why we call it tenths. So we have 700 plus 80 plus 5, and then carrying on from that spot, if you imagine a number line, we go 3 tenths of the way to the next number. And then from there, we go another 2 hundredths. So we divide that next bit into 100 equal pieces, and we only go 2 of those hundredths to the next piece. Then we got 0 thousandths and 0 ten thousandths, and then finally 900 thousandths at the end. And if you're uncertain about that, draw your place value chart that we did earlier on, fill this number in, and you will see 3 is in the tenths, so 3 tenths, 2 is in the hundredths, so 2 hundredths, and 9 is in the 100 thousandths, so 9 100 thousandths, like so. So there is that number in expanded form, but once again, we see 2 of these numbers don't actually do anything, right? The 0 thousandths doesn't move that number on the number line at all, and neither does the 0 ten thousandths. So we don't need to write them when you're writing expanded form. You can skip those over. But once again, Those zeros, even though we don't need to put them in expanded form, they are still essential. Why are they essential? Well, because this number here, 785.32009, is not the same as 785.329. You can't just not write the zeros. Those are different numbers. So the zeros are absolutely essential to write in the number, but in expanded form, they don't matter. And if you're wondering why are these two numbers different, why are they not the same, right? Why do those zeros actually make a difference? Well, the simple answer is that this number has 900,000ths in it, but this number, tenths, hundredths, thousandths, only has 9 thousandths. I say only, 9 thousandths is actually a bigger number than 900 thousandths, but we'll get to that later. So these numbers in their expanded form are different numbers, therefore they are not the same as each other. We are going to see some soon with some zeros that are the same number in expanded form and therefore are equal to each other. But so far we have two situations where the zeros, even though they don't have to be shown in expanded form, are critical in order to write the number correctly. Those zeros have to be there. Okay, trailing zeros. As promised, some zeros don't have to be there. So let's write the number 25.18 in expanded form, and then we're also going to write 25.18000 in expanded form. This is 20 plus 5 plus 1/10, if you think of your place value chart, and 8/100ths, again, if you think of your place value chart. This one over here is the same, and then a bunch of zeros. 0 thousandths, 0 10 thousandths, and 0 100 thousandths. And as we've been noting, in expanded form, those numbers, you don't need to include those zeros. They don't change. Zeros don't change anything when you add them, right? When you add a zero, it doesn't change anything. Well, look at the expansions of these two numbers. Unlike the one, let's back up here before I carry on. Unlike this, where this number has 900 thousandths, but this number has 9 thousandths when you write expanded form, so they are different numbers. Look at these two. They are exactly the same. 25.18 in expanded form, 20 plus 5 plus a tenth plus 1800ths, is exactly the same as 20 plus 5 plus a tenth plus 1800ths, this number here. So that means 25.18 is actually the same number as 25.18000. Those extra zeros after the decimal place at the end, trailing zeros we call them. The zeros at the end, so there's no more numbers, non-zero numbers occurring after them. Trailing zeros after the decimal don't actually change the number. So yeah, that's zeros at the end of a decimal do not change the number at all and are unnecessary. So 8.3 is actually the same as 8.30, the same as 8.300, and as many zeros as you want to add. They are all the same number. We'll get into this more when we start looking at our number line, but if you want to imagine this a different way that might help, imagine taking something and dividing it in a little section of line or something and dividing it into 10 pieces, and you go 3 of those pieces, 3/10ths. Now imagine dividing the same section into 100 pieces and you go 30 of them. That's just as much. Or imagine, let's go to pizza. Divide your pizza into 10 equal pieces and you eat 3 of them is exactly the same as dividing your pizza into 100 equal pieces and you eat 30 of them, right? Same thing. You've eaten the same amount of pizza. So trailing zeros after a decimal do not need to be there, and or we can add them when we need to. Say we have 8.3, but for some reason we feel like we need to write it with 5 decimal places. 8.30000 is the same as 8.3. Every single one of these numbers in an expanded form is 8 plus 3/10ths plus a bunch of zeros. Okay, So we're going to take these decimals and we're going to write each of them in the simplest way possible, meaning we're going to get rid of any zeros that don't need to be there. So on the first one, well, that 0 needs to be there because it's to the left of the decimal. And there's 3 trailing zeros at the end after the decimal. Those don't need to be there. So that number could just be written as 905.812. Next one, 702 million is what this number is. And everything is to the left of the decimal. We don't write the decimal. It's right there, right after the last zero. Every single one of those zeros, you can't just ignore those zeros because then you just have the number 702. They all need to be there. This one has some zeros after the decimal, but they are not trailing zeros, right? Because there's a 3 after them. So those zeros all need to be there. If you just drop those zeros out, this would become, and wrote 6.3, it would be 3/10ths instead of 3, what? Tenths, hundredths, thousandths, 10,000, 100,000, 3 millionths, I think. Did I do that right? 10, 100,000, 10,000, 100. Yeah, I think so. 3/10ths is not the same as 3 millionths. Unlike over here, this is still 8/10ths, 100th, and 2,000ths, right? Nothing changed by dropping off those zeros. And the last one here, these zeros are all important because you can't just move that 3 all the way over, but the trailing zeros after the decimal are not. So that would be the simplest way to write that number. Drop off any trailing zeros after the decimal. Okay, we're going to do some comparing numbers here. So we got some signs that allow us to compare numbers. We can say that numbers are equal, not equal. We can say one is greater than another or less than another, so bigger or smaller. And that's always left to right. You read that, greater than. So the left side is greater than the right side. The left side is less than the right side. And we also have these ones, greater than or equal to, and less than or equal to. Why do we have those separate things? Just very not an ideal explanation, but there might be some times when something has to be smaller than 100, right? You can't, if something gets to 100, then something bad happens. The nuclear processor overheats or something, right? You might have other situations where something can get to 100 but not go over 100. That's when you would use the less than or equal to sign. All right, so let's compare some things here. How does 18 compare to 15 plus 3? Well, 15 plus 3 is 18, so those are equal. If we want to write that in words, and this is something that your Math 052, 053 students are going to be asked to do all the time, you would write the sentence 18 is equal to 15 plus 3. Notice how they're going to make you turn everything into words, except you don't need to turn the numbers into words for these. So that's kind of helps a little bit. How about how does 7 compare to 10 minus 6? Well, we could do a few different things here, but what I want to focus on right for this line here is just to simply say they're not equal. 10 minus 6 is 4, so you would write that as 7 is not equal to 10 minus 6. Of course, you could also use the greater sign or the greater than or equal to sign in that case, but just showing how the not equal sign works just simply says two things aren't the same. That's all it says. Greater than, well, let's compare 15 and 8. 15 is, yes, bigger than 8, so that is a true statement. We would write that in words as 15 is greater than 8. Just to see that you don't always have to know what the numbers are, here we have an x, which is an unknown number on the left, and we're saying that it is less than 20. In words, x is less than 20. So we don't know what x is, but we do know that it has to be smaller than 20. Whatever that, in math, we use a letter when we don't yet know the value of something. And maybe we're trying to find out what that value is, or maybe we don't even care. But so you can have a situation here where you don't know what the value of x is yet, but you do know one thing about it. It has to be smaller than 20. Greater than or equal to, we're going to look at two things here because we could have something like this where the left side is definitely bigger than the right side. or something like this where they are equal. And both of those are true statements because 10 is greater than or equal to 8, because it's greater than 8. 10 is also greater than or equal to 10, because it's equal to 10. So it's the or is the key there, right? Greater than or equal. If it's either bigger than the right side or equal to the right side, true statement. And the same thing for less than or equal to. 200 is less than or equal to 500 because it's less than it. 200 is also less than or equal to 200 because they're equal. All right, so let's try dropping some greater than, less than, or equal to signs in here. Notice I've left out the or equal to options, so every one of these will, only one of these three things, yeah, I've left out the not equal to as well. Only one of these three signs will work for each of these. So compare 15 and 20. Well, 20 is bigger than 15, but since the 15's on the left, we got to use the less than sign. 15 is less than 20. Compare 12 with 15 minus 3. Well, 15 minus 3 is equal to 12, so we're going to pop an equal sign in there. Those are the same. Let's compare 20 with 12 plus 5. Let's see, 12 plus 5 is 17, which is smaller than 20. So we are going to use the greater than sign because 20 is greater than 17. 20 is greater than 12 plus 5. And here we look at, we see we've brought our trailing decimals in here. That 0 there doesn't need to be there, so this is actually 106.9. And none of those 3 zeros need to be there, so this is also 106.9. Those numbers are equal because they're both the same as 106.9. We got some more here. Oh, yes. So look what I'm doing on these. I have decimals that have a different number of decimal places. And it is very tempting for people to look, say, at this first one. And this is one they very often get wrong. So pay attention. Common test mistake. People look at this and they're like, well, 55 is bigger than 8. Or 455 is bigger than 48. That kind of thinking. And they say that the one on the right here is bigger, but what you need to do to compare decimals with different number of decimal places is make them all have all the same number of decimal places, and we know we can do that by adding any number of zeros, as many zeros as we want. So what I'm going to do is I'm going to add a 0 to that one on the left there, and I realize that it is actually 4.80. Now you can just sort of ignore everything and compare 80 and 55. 80 is bigger than 55, or 80 hundredths is bigger than 55 hundredths would be the proper way to say this, and therefore the left side is bigger. Over in this one here, we got 3 decimal places on the left and 4 on the right, so I could either add a 0 there, that would work, or I could notice that that last 0 doesn't even need to be there, so I think I'm going to do it that way this time. Yeah, I'm just going to drop that 0. So they both now have 3 decimal places. Now you can compare 302 to 200. 302 thousandths to 200 thousandths technically, but all you really need to do is think 302 versus 200. Oh, 302 is bigger. So this 17.302 is bigger than 17.200. And then the last one, 2 decimal places on the left, 4 on the right, so I'm going to add 2 there. There, now they both have 4 decimal places, and I'm comparing 1,500 to 2,961. Okay, the right side is clearly bigger, so this is a less than sign. So, comparing decimals, make them both have the same number of decimal places by adding zeros where necessary, then compare. Now, of course, that might not always be necessary. If this was like 2.8 and 4.55, well, obviously 2.8 is smaller than 4.55, right? Or if this was 6.8 and 4.55, obviously 6.8 is bigger, right? It's only when the whole number portion is the same that you need to look at those decimals. All right, rounding, I think our final topic here. So we're going to take this number 92,526,138. You could put that in your place value column if you wanted to. You could write it in expanded form if you wanted to. What we want to do is we want to round it first to the nearest 10,000. Okay, ones, hundreds, ones, tens, hundreds, thousands, 10,000. So it's that 2 we're looking at. So that's the first thing we're going to do. We're going to identify the number that we want to round, the number in that place value position is a 2. Then we're going to look just at the number that comes right after it and ignore everything else. So we're going to look at the 6 to help us round it. We don't care what comes after that 6. What comes after that 6, no matter what it is, whether it's zeros or nines or anything, cannot affect the rounding. So we're rounding the red digit, the 10,000s. We're doing that by looking only at the one that comes after it. If that number is a 0, a 1, a 2, a 3, or a 4, then that 2 rounds down and stays a 2. If it is a 5, 6, 7, 8, or 9, that rounds up because it's actually closer to 3. So 6 is 5 or above, so that 2 is going to round up to a 3. And then everything else after the 2, listen carefully, everything else after the 2 becomes a 0. So see again, let's follow the steps. We're going to round the 10,000s place. We identify what digits in the 10,000s. We look only at the digit that comes after it. We ignore everything else. When we decide whether that stays a 2 or goes up to a 3, we do that rounding and everything after the red digit becomes a 0, like so. Let's round to the nearest 100. So identify ones, tens. So it's a 1 is in the hundreds place. We're going to look only at the digit that comes after the 1. If that is 4 or less, which it is, that 1 stays a 1. So it rounds down and stays a 1. Everything else becomes zeros, including the digit, the blue digit that we use to help us round. Let's round to the nearest 1,000. Ones, tens, hundreds. So the 6 is in the thousands position. We are going to look only at the digit that comes after it in blue and ignore everything else. If that digit is 5 or up, the 6 would round up to a 7. If it's 4 or down, the 6 stays a 6. So it's a 1, so the 6 stays a 6, and everything after the 6 becomes a 0. Let's round to the nearest million now. So this 2 right here is in the millions place, marked in red. We're going to look only at the digit that comes after it and ignore everything else. If this digit is a 5 or up, we round that 2 up to a 3, which it is. So the 2 becomes a 3. Everything after it, including that blue 5, becomes a 0. Finally, let's round to the nearest 10. So we look in the tens place is the 3. We're going to look only at the digit after it. Everything else becomes a 0, but there is nothing else there. It's 5 or above, so that 3 rounds up to a 4, and everything after the 4 becomes a 0, like so. Notice, again, when you round, once you've identified, as we have in red here, which digit you're rounding, double check at the end that everything after that digit is a 0, because people will often round correctly, but then leave other digits in, especially the one that comes right after it. They'll leave in very often, the one that you used to help you round. Let's do some more rounding, but now with decimals. So to the nearest 10th. Okay, well, there's the ones column. There's the tens. One to the right is the tenths. So the 6 is in the tenths place. We are going to look just at the digit that comes after it and ignore everything else. If it's below 5, we round down. By the way, some people think, why is it seems a little unfair that at 5 you round up. But if you think about how many options there are for rounding up and rounding down, it makes sense. There's 5 for each. So you round up if it's a 5, 6, 7, 8, or 9. That's 5 options. You round down if it's a 4, 3, 2, 1, or 0. That's also 5 options. Okay, so that one says that the 6 is going to round down and stay a 6, and everything else turns into a 0, like so. But here's the little extra step with decimals, because we know that trailing zeros don't make a difference, so we don't have to write all those zeros like we did with the last examples with the bigger numbers. So we're actually just going to write 38.6. Let's round to the nearest hundredth. Where is the hundredths? It's the 1 right there. We are going to use the next digit after the 1 in blue to help us round and ignore everything else. 7 says that we round up, so that 1 becomes a 2, and everything after the 2 that we rounded becomes a 0. But we don't need trailing zeros after the decimal, so we just write 38.62. How about the nearest thousandth? That's tenths, hundredths. The 7 there is the thousandths. Now I've done this one very much on purpose. So there, it is tempting. I think I got a slide, yes. It is very tempting to see these 9s and say, oh, well those 9s, that rounds that 4 up to a 5. And then the 5 rounds the 7 up to an 8. No, remember, we look just at the next digit and ignore everything else. We do not compound round to make that 4 a 5. So we look just at the 4, and that says round down. So the 7 stays a 7. Everything else becomes a 0. But we don't need to write trailing zeros. And then the 10 millionth. Wow, okay. Tenths, hundredths, thousandths, 10,000ths, 100,000ths, millionths, 10 millionths. That 9 right there is the 10 millionths. We're going to use the digit right after it to round. Here is the one place you do have compound rounding, because that 9 says to take this 9 up, but there's nowhere to go. So that 9 sure goes up to a 0, but that flips over to the next one, because basically that 9 becomes a 10, right? How do you write a 10? Well, there's a 0 there, and the 1 has to carry over to the next one. So that 9 also goes up to a 10, a 0 here, and the 1 goes over to the next one. That 9 also becomes a 10, so a 0 here, and the 4 goes up to a 5. There we go, like so. Yeah. And then the trailing zeros don't matter. Oh, but they do in this case. Sorry. They don't matter, but we've been asked to round. Wow. We have been asked to round to the nearest 10 millionth. So in this case, you actually do show those zeros. I don't want to confuse you too much with that, but basically, you've been told show it rounded to the 10 millionth. If you don't show the 10 millionths, then you haven't shown your rounding. So this is the one case you would leave those trailing zeros in. And that is the end of our first lesson covering the review topics